Hello everyone. Today we will be discussing eigenvalues and eigenvectors. So let's begin with what exactly an eigenvalue and an eigenvector is. So an eigenvector of a square matrix, this is very important that your matrix must be a square matrix, is a non-zero vector x such that ax is equal to lambda x, and the eigenvalue of A is the scalar lambda corresponding to x. Now note that the eigenvalue is only going to exist if there is a non-trivial solution to your equation ax equals lambda x, because you can receive a trivial solution from any equation that you put forward just by making x equals to 0. And notice that we state that we are looking for a non-zero vector x. Which brings us to our eigenspace. Now the eigenspace is merely the null space of the matrix A minus lambda I. So this is going to be the set of all solutions of the equation A minus lambda I times x is equal to 0. Therefore, your eigenspace is going to consist of the 0 vector as well as all of the eigenvectors that correspond to lambda within your equation. So, let's move forward into how to actually find an eigenvalue. The first step to finding an eigenvalue in any equation is to start by finding A minus lambda I. So given a matrix A, you're going to start by scalar multiplying lambda with the identity matrix. Use just an arbitrary value lambda and subtract the product from A, forming a new matrix that's going to be of the form shown here. Once you find this matrix, you're then going to use it to find the determinant of A minus lambda I. You're just going to use basic properties of determinants and elementary row operations, at which point you're going to set your determinant equal to 0 to form the characteristic equation. Once you have your characteristic equation, you want to solve for lambda by factoring the polynomial that is produced. Lambda in this case will be your eigenvalue slash eigenvalues. Now once you have your eigenvalues, we can move forward into finding an eigenvector. So in order to find an eigenvector, the first thing you want to do is substitute the eigenvalues you found in the previous steps into A minus lambda I. Now you are then going to augment this new matrix with the 0 vector. Once you've augmented your matrix, you're going to use elementary row operations to reduce the matrix, and the null space that you then find after solving your system of equations will be the set of all eigenvectors for the given matrix. So for our example, we're going to work with just a example 2x2 matrix. Let's say this one here. The first step when finding your eigenvalues is to subtract from your initial matrix A lambda I, which will then give you once you have your A minus lambda I, you're going to find the determinant of your matrix, which, because this is a 2x2 matrix, is pretty simple. Now once you have your determinant, you're going to set it equal to 0 to form the characteristic polynomial, and factor your polynomial to solve for lambda, which will be your eigenvalues. Once you have your eigenvalues, you can then start to solve for your eigenvector by plugging your eigenvalues back into your A minus lambda I. Now, in order to solve for your eigenvectors, you are going to augment your matrix with the 0 vector as such. and reduce your matrix to echelon form. As you can see here, you end up with your x2 being a free variable, which means that in order to solve for your eigenvectors, you're going to have that x1 minus x2 is equal to 0, where x2 is free. Which means that 1, 1 is one of your eigenvectors for this equation, for your 1. Next, you're going to use your eigenvalue of 3 and repeat this process. Once again, you'll note that your x2 is free. However, in this case, x1 plus x2 equals 0. Which therefore makes -1, 1 your other eigenvector. One example in particular of how eigenvalues and eigenvectors can be used in real-life applications is through quantum mechanics and molecular orbital theory, as within the Hardy-Fock theory, the atomic and molecular orbitals can actually be defined by the eigenvectors of the Fock operator. The corresponding eigenvalues are then interpreted as ionization potentials via Koopman's theorem. This is only one of several practical applications of eigenvalue and eigenvector usage throughout the real world, as you can see here.